The next way to synthesize pyridine is from the reaction between 1,3-dicarbonyl compounds here and the 3 amino enones here. So in this approach, it is most versatile because it can be used to synthesize unsymmetrically substituted pyridines from a relatively simple precursors. So if you analyze the two starting materials used here, you can see that the nitrogen and carbon here is a part of enamine, so both of them are nucleophilic. And these two carbonyls are electrophilic. So in the mechanism of formation, the nitrogen or carbon may be used to attack the two carbonyl group. So let's say if we draw as a carbon attacking first, you are going to form I will leave the R group out. Okay, and from here, this can tautomerize back to the enamine. And this enamine can use the lone pair to attack here. And now you are going to form another enamine after you tautomerize. And from here, you can lose a molecule of water to generate the pyridine. As I mentioned that these precursors are easily prepared because the 1,3-diketone part, this usually are commercially available, or you may synthesize by using the Claisen condensation, either disconnecting here or disconnecting here. However, for the 3 amino enones, this one you need to prepare in advance. I don't think it is commercially available, but this can be easily prepared from the 1,3-keto ester or 1,3-diketones. So for this molecule, you can prepare it from the 1,3-keto ester and reacting with the ammonia. The ammonia will attack the more reactive ketones and forms the enamine, which is now becoming the 3 amino enones for the synthesis of pyridine here. So these two atoms can act as nucleophiles, and these two atoms can act as electrophile. And after losing 2 molecules of water, you are going to form 2 new bonds and complete the pyridine ring. The next example for the simple 1,3-dicarbonyl compounds, the 1,3-dialdehyde, if you want to synthesize this part, there is no substituent here, so the precursor that you actually want is the 1,3-dialdehyde, right? But this molecule is unstable, so we will use acetylenol ether as a protected aldehyde. So if you draw the mechanism, this one can be kicked out to form the oxonium ion, which can be electrophile, and you can also attack here, and then after addition elimination reaction kicking out this leaving group, you are going to form 2 new bonds as well, here and here. So you can try to draw a mechanism by yourself. Apart from the 1,3 dicarbonyl compounds, you can also use inones as the electrophilic precursors. So here you have the acid as a catalyst. So the oxygen here can be protonated by the acid, leading to the conjugate addition of the enamines to the conjugate system. And now you are going to form OH methyl. So this intermediate can tautomerize back to the enamine on this side, and then tautomerize back to the simple ketone on this side, and you are going to generate this intermediate, which you have the nitrogen as a nucleophile, you have the ketone here as the electrophile, just simply attacking here, and you are going to form the imine to complete the pyridine ring. In these examples, you can use nitrile as a group to activate to stabilize the enamine as well. So in this case, the cyanide is here. It doesn't do anything but to help stabilizing the formation of enamine here, and the reaction will use as normal the carbon here and nitrogen here to attack the electrophilic site here, and you have a leaving group ethoxide here. So you can draw the mechanisms, try to draw it by yourself, attacking here first, and then kicking out the leaving group, and after that re-tautomerize to form the enamine, and the nitrogen of the enamine attack the ketone. Apart from the enamine, you may use the amide here. So this proton is acidic, and you can remove the proton with a base. Just a weak base like potassium carbonate will remove the proton here to form the enolate, quite a stable one, and this can be used as a nucleophilic site to react with the more reactive ketone here, and you are going to form the aldol product first. And normally we know that the lone pair of the nitrogen here is not nucleophilic. However, since the ketone is so close and it is also in the same molecule, then the intramolecular cyclization is very very advantageous, and it will close the ring to form the 2-pyridone as a very stable product. So these are thermodynamically driven reaction. So far in the previous examples, we normally use the 1,3 dicarbonyl compounds as the electrophilic site, or it could be the enones with a leaving group attached to it here, or it could be the inone, right? Because these compounds have the right oxidation level to give you the pyridine straight away, But if you don't use these and then you use the enone instead, this one has lower oxidation level, and in the end you need to do something with it. For example, in this example, you use nitrogen here and carbon here to attack carbon here and carbon here. So after ring closure, if you draw the mechanism correctly, you are going to form this compound, which is non-aromatic. So how do you gain the aromaticity? Here you have the cyanide, which can act as a leaving group. So by eliminating it out, this will give you the 2-pyridone without the cyanide group. Or alternatively, if you have an oxidant, in this case, if you put some oxygen in there, the 2 hydrogen, so let's say from here you generate the same intermediate. Sorry, I forgot the hydrogen here. So you have the hydrogen here and also the hydrogen here. So if you put the air, it will oxidize these 2 hydrogen out, and then you are going to form the 2-pyridone with the cyanide still attached. The last type of reaction I want to show you is the cycloaddition for the formation of pyridine. The first type is to use oxazoles as a reagent to undergo cycloaddition with alkenes to form the pyridine. So if you draw the mechanisms, drawing the pericyclic reaction, cycloaddition, you are going to form the bicyclic intermediate, which can be so you see there is a proton here. This can, because there is a carbonyl group there, if you draw an E1CB mechanism, kicking out the O, then you are going to get this intermediate. And you know that you can remove the molecule of water here by elimination to form the pyridine ring. Apart from oxazoles, you can also use triacenes as the reagent to react with alkene to form pyridine. So the reaction first will undergo pericyclic cycloaddition like this. You are going to form another bicyclic intermediate here, and you can notice that here this almost becoming the nitrogen gas. So what you do with this is to undergo another pericyclic reaction. So this electron shift to here so that you can form the nitrogen gas, this one to here and this one to here. So you form 2 new double bonds here and kick out the nitrogen gas. Okay, and in your starting alkene, you already have a leaving group here. So you can remove this leaving group by elimination, and hence forming the pyridine that you want. In this last example, you can also use norbornadiene as a dienophile, and this is useful for the reaction because at the end you can eliminate cyclopentadiene to form the pyridine ring. And here is what I mean. So first of all, you are going to draw the mechanisms by the cycloaddition of alkene with the triacenes. So at this step, you are going to form the bicyclic intermediate. New group here. So in this part, okay, and as previous example, you are going to eliminate the nitrogen out by another another pericyclic reaction. And now you're going to form this molecule, and from here you can draw another pericyclic reaction. With this, you will complete the aromatic system of the pyridine ring here, because this will become a double bond, and you break the cyclopentadiene out from the reaction, forming the pyridine ring.